Here we go for another test on the first lesson, which is an outline of the basic structure of the atmosphere. It is very important for a pilot to know about the atmosphere simply because the pilot is flying through the atmosphere and the atmosphere is constantly changing, and it directly affects how the aircraft is operated for flight planning purposes. For example, how much fuel do you put on board for a particular flight? So this lesson will look at the structure of the atmosphere, and it will be a basic outline for the following lessons. The composition of the atmosphere is nothing more than a mixture of gases. In dry air, it is composed of 78% nitrogen and 21% oxygen. And that leaves 1% for the other gases. Those other gases are called the trace gases. They include argon, carbon dioxide, neon, helium, methane, hydrogen, ozone, and many other trace gases, but all totaled, they only come up to around 1%. And as far as aviation is concerned, they're pretty much insignificant. The atmosphere starts at the Earth's surface and it goes up to around 800 kilometers. When astronauts are re-entering the atmosphere, the spaceship heats up very significantly at around 125 kilometers. So astronauts would say the top of the atmosphere is around 125 kilometers. However, the atmosphere starts at the Earth's surface and it diminishes quite rapidly, and half of the atmosphere by weight is below 18,000 feet. And the top of the atmosphere has no well-defined upper limit. Included in that mixture of gases is water vapor. Water vapor is highly variable. It varies from a trace up to 4%. For example, if there was 4% water vapor in the atmosphere, it would displace all the other components of the atmosphere because the atmosphere is a mixture of gases. So if there was 4% water vapor in the atmosphere, there would only be 75% nitrogen and 20% oxygen. Now, as far as weather is concerned, water vapor is the most important gas simply because it can change from a gas to a liquid to a solid and vice versa under normal atmospheric conditions. Air has mass. Air is needed to sustain life. Supplemental oxygen is needed for flights above 10,000 feet if there's no pressurization. And pure oxygen above 40,000 feet is insufficient without pressurization. Air sustains an aircraft in flight. The wings or rotors accelerates a mass of air downward, and that produces an equal and opposite reaction on the wings or rotors and forces the aircraft up. And that's how come an aircraft flies through the atmosphere. Air is needed for the engine to produce thrust. Air has a mass of approximately 1.2 kilograms per cubic meter at sea level. There are many important properties of the atmosphere, but these are three very important properties. Mobility is a property that states a parcel of air can move freely about both horizontally and vertically with very little pressure difference. And it is a property of the atmosphere that we take for granted. Another property that's very important is expansion. Like any gas, a parcel of air has the ability to expand indefinitely if the pressure around it continues to drop. And the opposite of expansion is compression. If the pressure around a parcel of air increases, then that parcel of air compresses or increases in air pressure. In this diagram, it is a height pressure diagram showing how the air pressure decreases with height. At the Earth's surface, air pressure is approximately 1,013 hectopascals or millibars, which are the same units, and air pressure, as you can see from this graph, drops very rapidly right off the Earth's surface. And then higher up in the atmosphere, the air pressure drops less rapidly with height. However, near sea level, the air pressure drops approximately 1 inch of mercury for every 1,000 feet of ascent. And if we look at the height pressure diagram at 18,000 feet, air pressure is approximately 500 hectopascals. So in other words, half of the atmosphere by weight lies below 18,000 feet. So if a balloon that rose from sea level up to 18,000 feet would double in volume. And if that balloon went from 18,000 feet back down to sea level, it would drop in volume or decrease in volume by 1/2. The atmosphere is divided up into layers depending upon temperature, because in meteorology, temperature is a big factor. The lowest layer of the atmosphere is called the troposphere. The next layer is the stratosphere, and the next layer is the mesosphere. And the top layer of the atmosphere is the thermosphere. And as you can see with this temperature profile, the temperature drops in the troposphere, rises in the stratosphere, drops in the mesosphere, and rises in the thermosphere. And this temperature profile line is called the International Standard Atmosphere Temperature Profile. It is an average of temperature in the atmosphere over many, many years at 45 degrees north. Now, the layer that divides the troposphere from the stratosphere is called the tropopause, and in the International Standard Atmosphere, the tropopause is found at 36,000 feet, or flight level 360. And the nickname for the tropopause is called the trope. Now, the International Standard Atmosphere is an average of temperature, pressure, density, and speed of sound over many years at 45 degrees north. It has hundreds of uses. The pilots use it mainly for aircraft performance baselines. The parameters of the International Standard Atmosphere that you must memorize are sea level temperature of plus 15 degrees Celsius, sea level pressure 29.92 inches of mercury. The temperature drops 2 degrees Celsius per 1,000 feet in the troposphere. The tropopause, or trope, is at 36,000 feet. The trope temperature is minus 56.5 degrees Celsius. And the temperature remains constant from the trope up to 65,000 feet. Above that, the temperature increases with height. Now, this is a diagram of the International Standard Atmosphere, where the temperature at sea level is 15 degrees Celsius, and the temperature drops 2 degrees per 1,000 feet in the troposphere up to 36,000 feet, or 11 kilometers, and then the temperature remains constant at minus 56.5 degrees Celsius up to 20 kilometers or around 66,000 feet. And above 20 kilometers, the temperature increases with height. Now, this is an example of a subset of the International Standard Atmosphere, and an example of one use of the International Standard Atmosphere. The mechanic that does the airworthiness inspection on the aircraft uses a chart like this to check the altimeter. He or she connects the altimeter to a machine and then adjusts that machine to read 20.577 inches of mercury. And that altimeter better read 10,000 feet, because if it doesn't, it needs to be serviced. Now, the International Standard Atmosphere is only an average over many, many years at 45 degrees north, and on this diagram, that is represented by the blue line. On any given day, at any place, the temperature is not going to be identical to the International Standard Atmosphere. Now here at Yarmouth, Nova Scotia on November the 6th at 1200 Zulu, the temperature at the Earth's surface was 0 degrees. The temperature increased with height from the surface up to 1,000 feet. Now that is called an inversion, and because it happens at the Earth's surface, it's called a surface inversion. It is an inverted temperature trend. The temperature normally drops with height in the troposphere, but if it increases with height, then that is called an inversion. And of course, if it happens right off the Earth's surface, it's called a surface inversion. So here we have an inversion between 4,000 and 5,000 feet. And then between 5,000 and 6,000 feet, there's no change in temperature with height, and we call that an isothermal lapse rate, or no change in height. And then the temperature drops with height above 6,000 feet. And higher up in the atmosphere, notice how closely the temperature resembles the International Standard Atmosphere. And the height at approximately 30,000 feet, where the temperature becomes nearly isothermal, is called the tropopause, or nicknamed the trope. And in this case, the trope is at 32,000 feet. Now here we have what we call a tephogram, or a height temperature diagram, and it is for Kelowna, BC on November the 3rd at 00 Zulu. The temperature at the surface is 11 degrees because Kelowna is not at sea level, and the temperature drops with height. And where the temperature becomes 0 degrees, and in this case it is at 6,000 feet, is called the freezing level, and above that the temperature remains on the minus side. Now, if the temperature at the Earth's surface is below freezing and remains below freezing all the way up, then we say that the freezing level is at the surface. Now, why does the temperature rise in the upper part of the stratosphere? That is because there is a high concentration of ozone in the upper part of the stratosphere. Ozone is 3 oxygen atoms stuck together to make an ozone molecule. And ozone intercepts ultraviolet radiation from the sun. And any mass that absorbs electromagnetic energy, or in this case, ultraviolet energy, has its internal temperature go up. And that's why the upper part of the stratosphere is relatively warm, such that at the stratopause, the temperature varies from minus 15 to near 0 on some days. Now, where did the name troposphere come from? Well, it is derived from a Greek word tropos, which means churning, overturning, and mixing. And that's exactly what happens in the troposphere. There is lots of horizontal and vertical motions and mixing on most days. The stratosphere is also derived from a Greek word strata, meaning everything is in layers. There's no vertical motion, just horizontal motion. Now, the presence or absence of vertical motion in the atmosphere is totally dependent upon temperature structure. An increase in temperature with height or no change in temperature with height prevents vertical motion, and a decrease in temperature with height favors vertical motion. Now, in this picture, we're flying on top of a deck of cloud, and you can see that the top of that cloud is rather bumpy, and that's simply because there's lots of vertical motion going on. Now, in this diagram, we have two lines, a red line that represents a real warm air mass like one over Mexico or Brazil, and a blue line that represents a really cold air mass like over Nunavut in January. Now, the blue line, the air pressure starts out slightly higher at the Earth's surface, but very quickly drops with height, such that the pressure is lower at any given height in the cold air mass compared to the warm air mass. So we have a purple line here that represents 18,000 feet in the atmosphere, and that is a height, not a height that you see on the altimeter in an aircraft, but a height that you would measure with a tape measure. It is a geometric height, a specific height on Mount Everest. So in the cold air mass, the pressure is lower, and in the warmer air mass, the pressure is higher. And so air has a high degree of mobility, so the air pressure would want to blow from the warm air mass to the colder air mass at any given level, and that's what starts the wind. Now, this diagram pretty much explains the same thing. When an aircraft is flying at 5,000 feet, on the altimeter, it is flying the 5,000 foot pressure level. The altimeter senses a pressure outside the airplane, and it relates that pressure to a given altitude based on the International Standard Atmosphere. And so when the altimeter senses a pressure of 24.9 inches of mercury, it is going to show 5,000 feet. So if you were flying 5,000 feet from a very cold air mass to a very warm air mass, then that pressure level just gets higher as you go along. Now, in a very cold air mass, Nunavut in January, and you're flying 5,000 feet on the altimeter, if you were to measure your altitude with a GPS or a tape measure, then you would find that you are flying a lot closer to 4,000 feet. Now, if you were flying in a real warm air mass and 5,000 feet on the altimeter, and you measured your actual altitude with a GPS, then you would find that you are flying a lot closer to 6,000 feet. And so the same story is true if you're flying at 10,000 feet, because all you're doing is flying the 20.6 inch pressure level. You are flying the 10,000 foot pressure level. And if you go from a cold air mass into a warm air mass, your actual altitude or GPS altitude would get higher. And if you were flying at 18,000 feet on the altimeter, you are following the 14.9 inch pressure level. And again, flying from a cold air mass into a warm air mass, your actual altitude would be progressively getting higher. And if the temperature of the atmosphere was identical to the International Standard Atmosphere and you had 18,000 feet on your altimeter, then the GPS would be showing 18,000 feet as well. So the bottom line here is all pressure levels are higher in a warm air mass compared to a cold air mass. And if that is true, air has a high degree of mobility, so the higher air pressure over here at any given height would want to blow towards the lower pressure in the colder air mass, and that's what starts the wind. Now, the tropopause in the International Standard Atmosphere, as we have learned, is at 36,000 feet, and the tropopause has a temperature of minus 56.5. But that varies depending upon the temperature of the air mass. Now, in a very cold air mass, the tropopause could be as low as 25,000 feet, and the tropopause temperature minus 45. In a very warm air mass, the tropopause could be as high as 55,000 feet, with a trop temperature much colder, minus 70 or maybe minus 75 degrees. Now, this slide shows the tropopause temperature and height. And of course, it's for January the 16th, 2009. Over northern Canada, the height of the tropopause is around 25,000 feet, and the tropopause temperature around minus 45 degrees. And down over Brazil, the tropopause height is at 55,000 feet, and the tropopause temperature minus 75. So in a very warm air mass, the trop height is quite a bit higher and quite a bit colder. In the real cold air mass, the trop is very low, or relatively low, and the trop temperature is relatively warm. The properties of the troposphere, as we have learned, the temperature usually decreases with height, and if it doesn't decrease with height, it is called an isothermal lapse rate or an inversion, one where the temperature increases with height. Pressure decreases rapidly right off the Earth's surface and then less rapidly at higher altitudes. Right off the Earth's surface, near sea level, pressure decreases 1 inch of mercury for every 1,000 feet, but that's just an approximation. Moisture exists in the troposphere as a vapor, liquid, or a solid, and it can change back and forth through all of those three states, and that's what causes the weather. There's lots of vertical and horizontal mixing in the troposphere, and that's why we call it the troposphere. And that vertical and horizontal mixing causes turbulence, or the bumps, when you're out there flying. Almost all weather activity occurs in the troposphere. The wind usually, and I stress usually, increases with height, with a maximum wind speed just underneath the tropopause. And the top of the troposphere is called the tropopause, or the dividing line between the troposphere and the stratosphere is called the tropopause. Now, in this picture, we're flying in the lower part of the stratosphere at 40,000 feet. And the top of the clouds is the tropopause, or the top of the troposphere. The properties of the stratosphere are: it begins at approximately 36,000 feet, but it is where the temperature becomes nearly isothermal with height at that altitude. The temperature increases with height above 65,000 feet because of the high concentration of ozone absorbing ultraviolet radiation from the sun. The temperature at the top of the stratosphere varies from minus 15 to near zero. On average, the temperature at the bottom of the stratosphere is minus 56.5, and because of its temperature structure, there's no vertical motion. Wind usually decreases with height from the tropopause upward, and there's no cloud and no weather. In this picture, taken from the window of the space shuttle, is Hurricane Elena. And at the limb of the Earth, you can see a thin blue line. Well, that represents the atmosphere. It is the troposphere and the stratosphere. And if you compared the Earth to an apple, the troposphere and the stratosphere is about as thick as the skin on that apple. Now, there's not enough molecules of air in the mesosphere and the thermosphere to reflect light, so it appears black in this picture. Now, this is the end of Lesson 1, and we ended with a picture that we began with. And so over on the right-hand side, we see some clouds. And those clouds are topping out at the top of the troposphere, or the tropopause. And so the orange in this picture basically represents the troposphere. And above that is the stratosphere. And that's the bright blue. And above the bright blue, it gets darker and darker and darker. And that represents the mesosphere. The thermosphere is, of course, totally black.